Okay, welcome to the final class of Sci 118 astronomy. I did not expect to be recording this. Unfortunately, we had a bit of a weather issue this morning, and unfortunately, our final class was canceled. And as far as I know, there's no way to really reschedule this type of thing. So I'm recording this, our final lecture, which is about an important topic. And so let's go through this chapter, kind of wrap things up. This chapter is all about the topic of cosmology, the idea of understanding how this all came about. And in order to have this all come together. We need a we need a model. We need an idea, theory to tie all this together. How did all this that we observe around us in the universe? How do we get this all how did this come about? And so that's what cosmology is really about. This whole sort of area of astronomy. And we touched on this in our lab last week. We were talking about the age of the universe. If we know that the universe is expanding, if the universe is very, very large and expanding now, well, if you're able to turn the clock backwards, if you're able to get into a time machine and travel backwards in time, well, that means the universe was much smaller in the past. And if you keep going backwards, all the way to the very beginning, well, the all the matter and energy in the universe is compressed down to a single small volume of space. And so the universe becomes very, very hot and extremely energetic. And that's the process that we call the Big Bang. The Big Bang theory is the best idea that we have at this point about how the universe got started. And there's a lot of unanswered questions. Certainly in this session, in this chapter, we can't answer all the questions about where did the universe come from. But this is our best effort at this point. And, well, when did this Big Bang occur? Well, we can, at the very least, we can use Hubble's law and we can calculate T, the age of the universe, as we did in the lab. If you know what the Hubble constant is, you can convert the Hubble constant into a time for this particular equation to work. If you rearrange Hubble's law, you can write it as T equals 1 over H, or H naught, as it sometimes is written. And so if you know what H is and you convert it into a time, you can estimate the age of the universe. And so our best estimate for the Hubble constant at this point is around 73 or 74. And so if you use that, the age of the universe turns out to be about 13.8 billion years ago. So the Big Bang occurred almost 14 billion years ago. And I think for most of you who did the lab, you got an answer that was pretty close to that. So it works out pretty well. So that's our best estimate of the age of the universe is about 14 billion years old. So consider that we know from looking at things like meteorites, we know that the solar system and the sun, all the planets and the sun are about 5 billion years old. That means that we're relatively new to the universe. The universe was around for several billion years before the sun formed, and so we're kind of the new kids on the block. And so we have to consider, how is the universe expanding? What could change the expansion of the universe? Well, certainly we could slow it down with gravity. If gravitational pull, if there's enough matter in the universe, the gravitational pull of the matter in the universe would be able to slow down the expansion of the universe over time. And so one of the main reasons that the Hubble Space Telescope was built was in order to measure the distances to these type 1a supernova, these standard bulbs or standard candles, as they're called. We know what their brightness should be. And so if we measure the brightness and to estimate the distance to these type 1a supernovas, uh, if they appear brighter than we expected, well, that means the universe is slowing down. The expansion is slowing down. But what we actually found was that these supernova were fainter than we expected, which means that the universe must be accelerating. Those supernova further away than we originally expected, which was a big surprise. No one thought that the universe would be accelerating in terms of its expansion. This was a big surprise to just about everyone. And how could this be possible? What could be possibly making the universe expand faster than is expected? So the universe can't just accelerate on its own. You have to have something to accelerate. There's got to be some energy that expands the universe. And it turns out that if you take an empty piece of space and you pull everything out of it, pull every speck of dust, every molecule, every atom, pull it all out until you're left with absolutely nothing in that space. Well, it turns out there is still energy. The space itself seems to have this property where there is an energy in space itself. And that's referred to as dark energy. And that's a little bit confusing. I think personally they probably should have picked some other kind of name for this because it's a little bit confusing because we just discussed dark matter, and then you have this dark energy, but they're not, these two concepts are not really related. There's no relationship between these. So this is a completely different concept that goes by a similar name, which is kind of unfortunate, but that's the name that is generally used. There's this dark energy in the space itself. And early on in the history of the universe, after the Big Bang happened, it doesn't really seem to play very much of a role. It doesn't have much effect on the expansion of the universe. But all of a sudden, about 7.5 billion years after the Big Bang, and here's a close-up shot of a diagram from the textbook, about 7.5 billion years after the Big Bang happened, well, then all of a sudden, dark energy kind of kicks in and the universe starts to accelerate. And so it doesn't happen, the effect isn't apparent really until the 7.5 billion years passes. So the universe at this point is about halfway through its current age. And so it kicks in, and then now that's what we see when we take, let's say, our space telescopes and we measure the distances to those supernova. It seems that the universe is now expanding a little bit faster than we originally expected. And like I said, that's a surprise. So we live inside this expanding universe, and we want to come up with some kind of model to explain what was the universe like in the past, what will it look like in the future. And so we could have some different types of expanding universes. And so here's a couple of different models. There's also a diagram, I believe, that's used in the textbook. Any kind of model that we come up with for the universe, it must include some kind of expansion, of course, because that's what we see all around us. It must be homogeneous and isotropic, as we've said. Homogeneous, it's relatively smooth. Yeah, it's lumpy on the small scale. You see these clusters of galaxies and voids and things like that. But overall, largest scales of the universe, it's relatively smooth, so to speak. It's isotropic. It's the same in all directions. So that's what our model has to, that's the properties it has to have. You could have a universe that's decelerating, one that is not expanding forever. And that's the first two models that are shown here. One that's really interesting is this one on the left-hand side. You have the Big Bang happening, the universe expands, but it has a lot of matter in it. And that's not only slows down the expansion of the universe, eventually starts to collapse it, and the universe collapses back down. This is sometimes referred to as a big crunch. So the universe starts out with a big bang, ends with a big crunch. And that's a closed, often referred to as a closed universe. You also could have a universe that's uh, expands initially, but then the expansion slows down, and that's the next model over. You also have a coasting universe. You can have a coasting universe that expands forever. And then you could also have an accelerating universe where the universe expands very, very rapidly, is dominated by dark energy and expands very, very rapidly and expands forever. So how do we figure out, well, what kind of a universe do we live in? And in order to do that, in order to try to understand what kind of universe we live in, well, the easiest way to do that is to look at the density. Look at the density of the universe. If you imagine material in the universe is spread out relatively smoothly, it's homogeneous. Um, the more matter that you have, the more gravity you have, and the slower the expansion is going to be. And so, as we mentioned, there can be closed universes, this high density universe where there's so much matter that the gravitational pull of everything inside it makes the universe collapse. And so, on this diagram, which is also in the textbook, uh, take a look and you can see here's the Big Bang. This is the red line in this chart is the high density closed universe. And so the Big Bang occurs over here. As time goes on, eventually the universe collapses and here's your big crunch. We can basically rule this out. This universe can be ruled out because we just don't see that much mass in the universe. Um, then you have the accelerating universe. There's the green line is the accelerating universe, and that is a very low density universe. Not only is it low density, it also has a lot of dark matter, dark energy in it. That dark energy accelerates the universe and it expands very rapidly forever. Um, you also have low density universes that are not quite as extreme. That's the blue line that is shown here. This also will expand forever as well, just not as quite as quickly as the accelerating one. So these are both considered open universes. We can kind of rule out these low density ones as well. As we look around us in our local area, we can see what the density of the matter is. And it seems like this is not our case either. So when we look out into the universe and look at our density, what kind of universe do we live in? Well, I believe it's purple. It's hard to see the color here, but the purple line here is the case of the critical density universe. And it's kind of right on the border. It's right on the boundary between an open universe that's the low density ones. And you have the closed universes, which are high density. We're sitting right on the edge. We're sitting right at this critical density between these open and closed universes. And it is described as as a flat universe. And we don't mean that it's literally flat, like a flat Earth theory or something like that. This is a flat universe because this universe has the geometry that we're all familiar with. You look at a triangle, all the angles add up to 180 degrees, the Pythagorean theorem. If you'd have two parallel lines, if you draw two parallel lines, those two parallel lines will never meet. We live in this flat geometry, this universe that has a flat geometry. And it's all the geometry that we're used to and is familiar to us. And so that's what universe we seem to live in. We live in this critical density universe that is kind of on the boundary between open and closed. And so this universe will continue to expand. And it eventually will stop expanding, but it won't stop expanding until you reach almost infinity, and the infinitely time, this infinite time in the future. And so it's kind of a weird um, situation. But it seems to be this is the universe that we live in. When we look at the density of the universe, it tells us that we live in this critical density universe that is considered a flat geometry. And so it is expanding. And so you might wonder, well, what is the universe expanding into? Uh, and so it's a kind of a natural question. And it's a little bit hard to answer because we're very limited in how we can perceive the universe around us. Imagine being an ant, and not only just an ant, but a two-dimensional ant. Imagine you're a two-dimensional ant. You know about left and right and forward and backward. That's your world. That's the only thing you know is two dimensions. Uh, to left and right, forward and backward. That's fine. Those are your two dimensions. And imagine you live on a round universe. You live on a ball, a universe that's shaped like a ball. As you walk around on the surface, it seems two dimensional to you, but you're not really aware of that third dimension. You can walk all the way around it, and the your universe has a limited size to it, but it has no boundaries. You could go around and around that ball and never reach an edge. So the universe kind of seems infinite to you, but it's really not. We plainly can see that the size of the ball. We can see it because we're three-dimensional creatures. We not only know about left and right and forward and backwards, we know about up and down. We're a three-dimensional. We live in a three-dimensional situation ourselves. So we can see it easily, but the ant can't. He's a two-dimensional creature. He can't just look up and see us looking down at him. It's a direction that he's not really aware of. And that's our situation. We live in a we feel like we live in a three-dimensional world, but that may not be the whole story. So how can uh, really understand what the universe is expanding into? Because there's only three dimensions that we can conceive of. And so that's almost impossible a question for us to really answer, at least at this point. We can describe it in mathematics, we can describe higher dimensions, but it's not something that we can really understand. We can really wrap our brains around them, just like that two-dimensional ant can't really just look up because it doesn't really understand that direction. And if you consider it on the left-hand side here, we have a diagram of the three dimensions that we're familiar with. If you want to add a fourth dimension to this, well, then you have to add a direction that is 90 degrees to all of these directions, and that's kind of impossible. Our brain can't really do that. So it's almost impossible for us to really imagine this kind of thing. So as the universe is expanding, what is it expanding into? Well, we really don't know. And people talk about perhaps other universes existing out there, but that too is also very difficult for us to really imagine what that is like because we're limited into how many dimensions we can understand. But as the universe is expanding, it seems like the universe will, even though the expansion will continue uh, for a very, very long time, as I said, it kind of does technically stop at infinity, but as far as we're concerned, well, that's almost forever. And so it'll continue to expand. And the idea of this dark energy strengthens this idea that the universe will continue to expand over time. The density of the universe is at this critical density. So what's going to happen in the future? And so here you see a picture on the right-hand side here, a picture of galaxies from the Hubble Space Telescope. These are very distant galaxies. Well, over time, the distances between these galaxies will increase, of course, and they'll get further away and they'll get fainter and fainter and fainter. Eventually, the stars in those galaxies will burn out. Even those little red dwarf stars, which live a very long time, eventually those also will burn out as well. And so the distances gradually increase between the galaxies. They get fainter and fainter. The stars inside of them eventually get fainter and will burn out and cool off. They end up as these black dwarfs, or the big stars end up as black holes. The gas and dust in the universe eventually is all used up. And so the future of the universe might look like this: almost complete blackness, sometimes known as the Big Chill, or the big freeze is sometimes how it's referred to. And that is, how far away would that be? When would the Big Chill occur? It's 10 to the 100th power years from now. The universe will be very cold and very, very dark. Kind of a depressing thing to think about. But, this is what we think is the future if the universe continues to expand forever, or almost forever. You end up with this very dark universe. And so, as the universe is expanding, uh, the universe is expanding. So how big is it now? In the future, be extremely large, of course, but how big is it right now? We know that the light from the most distant galaxies that we know of has traveled about 13.8 billion light years. That's that look back time we've talked about. At the speed of light, the light is traveling across the universe. And so from the furthest parts that we can see, the universe is about 13.8 billion years old. And so therefore the light has traveled about 13.8 billion light years to reach us. And so you might be tempted to take that 13.8 and multiply it by 2. And that would give you the size of the universe. And that's might be a logical way of doing it, but remember that during that time, while the light is traveling across the universe is still expanding. So the universe is actually larger than that. So you might assume that it's 27.6 billion light years across. Yeah, okay, that's a good estimate, but we've left out the fact that the universe is expanding during those 13.8 billion years that have passed. So if you add in the expansion, well, how big is the universe? It's been expanding for 13.8 billion years. And so if you add that in, you find out that the universe is approximately 93 billion light years across, is the current size of the universe. And so that's our best estimate, almost 100 billion light years across, and getting larger. Every second that goes by, it's getting a little bit larger. So that's our current estimate of the size of the universe, 93 billion light years. Pretty amazing, pretty big. And so this is where this whole idea of the beginning of the universe, how did the universe get started? Turn the clock back, and the universe, it must have been much smaller and very, very hot. And so how did the universe start? Well, the very first moment of the Big Bang, we really don't know. We don't have the physics, really. We don't have the information that we need to really say how the universe got started. But we've been able to probe back pretty far. And we have at this point, seem to have at least a halfway decent handle on what the first few minutes of the universe are like. So putting that aside, that we don't really know how the Big Bang got started, we certainly have some good observational evidence of what happened within the first couple of minutes. Within the first couple of minutes, the temperature is dropping very rapidly. The universe is expanding at that point. After 0.01 second, a hundredth of a second, the temperature of the universe is 100 billion Kelvin. After about 3 minutes, after that 3 minutes pass, well, then it drops down to about a billion Kelvin. And then after 100,000 years, about 3,000 Kelvin. During this period, the universe is so hot that it's dominated by radiation. There really nothing, no matter exists at this point. And energy and matter can be converted into each other. It's just E equals mc squared. And you have these very, very high temperatures. And so the early universe, nothing really exists except for radiation. And so radiation dominates the universe very early on during this high temperature period. And here's a little close up, a little timeline here, diagram from the from the textbook. And so, um, the first protons and their antiparticle, the protons, form about a thousandth of a second after the Big Bang. The first atoms don't form until here, 10 to the seventh seconds. And then galaxies form and stars form, etc., as time goes on. And during this early period, as we mentioned, radiation is kind of dominating the whole universe until these particles start to form. The universe has to cool down enough for the ordinary particles that we understand, like protons and neutrons and electrons. It takes a little bit of while here for the universe to be cool enough for matter to actually exist. And so we've traced the history of the universe back to about 10 to the negative 43 seconds. That's the earliest time that we know of in the universe at this point. That's kind of the limit of our physics. You can go back to 10 to the negative 43rd second. Eventually, though, as we said, the universe does start to cool off, and you end up with ordinary particles like electrons and protons, and that sort of thing starts to form. And so it takes about 3 minutes for the universe to start to cool down enough where stuff that we are familiar with starts to exist, stuff like a helium atom or a hydrogen atom, something like that. So it takes about 3 minutes for the universe to kind of cool off. And then the universe becomes a little bit more normal at that point. And so we get atomic nuclei will form. There's actually the fusion that was taking place just in open space. The universe is so hot still, as even though it's cooled off a little bit, there's fusion just simply occurring just out there in open space. But that ends after about a minute, about 4 minutes after the Big Bang. The universe cools down enough that that type of fusion stops. And we can look at this deuterium, this heavy hydrogen that we've mentioned on occasion during the course. You've got this type of hydrogen here, this deuterium. If we look at that, this gives us an idea of what the density of the early universe is. And so that's a nice clue to what was happening early on when the universe was first formed. And so, how do we test this idea that the universe was very hot early on in its history? If we come up with this Big Bang theory, what kind of prediction does this make? Well, one critical time period is about 380,000 years, 380,000 years after the Big Bang. That's a really critical moment in the history of the universe, because at that point, after 380,000 years have passed, well, then those electrons and protons that have appeared will start to combine and form the sort of ordinary atoms that we're familiar with. And so this is the moment that the universe actually becomes cool enough that it's actually transparent, that light can actually travel through space over large distances. And so this is kind of a period of time, this 380,000 years is sometimes referred to as the Dark Ages, because atoms are starting to form. But at this point, there are no stars yet. There's no galaxies, there's no planets, nothing like that existed. So the universe is really becomes very dark. It starts out very hot, lots of radiation, but all of a sudden it reaches this point at 380,000 years and it becomes transparent and it is very dark. And so this matter and radiation becomes decoupled as the cosmologists describe it. And the light can travel through the universe in a way that we would recognize. And this light, the first light that travels through the universe can still be detected today. We so we it, Big Bang Theory makes this prediction that we should be able to see this ancient light uh, in the universe. And sure enough, we do. And we've mentioned this. I mentioned this when we were in the planetarium last time. It's really kind of interesting uh, that the best evidence that we have of the Big Bang was discovered right here in New Jersey. Uh, as I mentioned, there's an antenna that's known as the Horn antenna, located in Holmdel, New Jersey, right off the Garden State Parkway. And two scientists, Penzias and Wilson, Robert Wilson actually still lives in the Holmdel area, and they used this radio telescope. They're working on satellite. They were working on satellite communications, is what they were working on, and they detected this noise in the background, in the microwave background, and it was kind of a glow, a radio glow in all directions in the microwave wavelengths, and they couldn't get rid of it. And eventually, talking to the people at Princeton University, realized that, oh, well, this is the radiation that the Big Bang predicts. Uh, there should be a glow in all directions in the microwave at this point, uh, due to this light, this ancient light coming from the very first moment, that 380, I should say first moment, that 380,000 years after the Big Bang, when you reach this moment that ordinary neutral atoms are forming there in the universe. And so this was a critical moment, and this is one of the best evidence that we have that the Big Bang actually happened. You can point these telescopes or you can point a satellite in any direction. You can pick up this background radiation there. So this is how we know uh, that the Big Bang occurred. And so here we have a map that was made with a NASA satellite back in the 1990s. They measured the background radiation, this microwave energy. They pointed this satellite in all directions over the entire sky, and you get the temperature of 2.7 degrees Kelvin. And this is exactly what is predicted by the Big Bang. You should detect this radiation in all directions, and the temperature should be about 2.7 Kelvin. And it's very, very smooth, the background radiation, when you point it in different directions. It's very smooth, but not completely smooth. As you look, they've color coded the map here, and it shows you that there are some uh, spots where it's a little bit, the temperature is a little bit higher than average, excuse me, and there's some cold spots as well. And so this is what gives rise to the structure in our universe. And so we can see that it's not completely smooth, and some of these areas will give birth to these galaxies and galaxy clusters and things like that. So this is, as I said, is our best evidence that the um, uh, Big Bang actually occurred. And we had also had a follow-up mission called the Planck satellite in 2015 that did even more precise measurements and further kind of strengthened this idea that we live in this density, this universe. It confirms our ideas about the density of the universe. The density of the universe is at this critical density, that the age of the universe is about 13.8 billion years. The dark energy, it's expanding. The way that it's expanding is the dark energy content is about 68%, so close to 70% of the universe is this is mysterious dark energy. And the matter content, if you take all the ordinary matter that we see in stars and galaxies and that sort of thing, add in the dark matter as well, and the energy, that makes up about 32% of the universe there. 68% is dark energy, 32% of the universe is some kind of matter. And so that means that only 5% of the matter in the that we have in the universe is the ordinary stuff that the Earth and human beings are made of. And so that's kind of an amazing result. But this kind of just all confirms our ideas about how the universe got started. And so this just is just a different chart that kind of shows you, again, this is in the textbook, and shows you what the percentages are of the matter and energy that are in the whole universe. Dark energy, 68%, dark matter, 27%, and the ordinary matter is about 5%. And so all this stuff that we've been studying in this course, the planets, the stars, nebulas, galaxies, that's only a tiny little bit of the universe here. And so this is kind of a nice timeline of if you put it all together, you have the Big Bang occurring at time 0 at the left-hand side of the chart here. The universe expands very rapidly early on. Eventually you get ordinary, as we said, it's very hot. There's radiation dominating the early universe. But finally, some ordinary particles like protons form. There's fusion occurring in sort of empty space here. That doesn't last very long. And after about, as we said, 380,000 years, that's where that first light is able to start traveling through the universe. And that's what we detect today as this cosmic background radiation. Eventually, though, stars and galaxies do start to form. That takes place about 200 million years or so, which is very early. It's a little bit hard to explain how fast this has occurred, how fast stars and galaxies start to form. And so that's a little bit hard for us to explain at this point. But we think that's the first stars and first galaxies, about 200 million years after the Big Bang. And then at some point, about 7.5 billion years after the Big Bang, dark energy starts to accelerate the expansion. And at 13.8 billion years, this is where we are now. And here's just a close-up shot of that whole process, that 13.8 billion years. And so you can take a closer look at this diagram here. Kind of describes that. And this is the critical point. This 380,000 years is where that cosmic background radiation comes from that was discovered right here in New Jersey. And so this is kind of the history of the universe in a nutshell.
The beginning of everything, the Big Bang. The idea that the universe was suddenly born and is not infinite. Up to the middle of the 20th century, most scientists thought of the universe as infinite and ageless. until Einstein's theory of relativity gave us a better understanding of gravity and Edwin Hubble discovered that galaxies are moving apart from one another in a way that fits previous predictions. In 1964, by accident, cosmic background radiation was discovered, a relic of the early universe, which together with other observational evidence made the Big Bang the accepted theory in science. Since then, improved technology like the Hubble telescope has given us a pretty good picture of the Big Bang and the structure of the cosmos. Recent observations even seem to suggest that the expansion of the universe is accelerating. But how did this Big Bang work? How can something come from nothing? Let's explore what we know. We can ignore the beginning part for now. First of all, the Big Bang was not an explosion. It was all space, stretching everywhere, all at once. The universe started very, very, very small and quickly expanded to the size of a football. The universe didn't expand into anything, space was just expanding into itself. The universe cannot expand into anything because the universe has no borders. There is, by definition, no outside the universe. The universe is all there is. In this hot, dense environment, energy manifested itself in particles that existed only for the tiniest glimpses of time. From gluons, pairs of quarks were created, which destroyed one another, perhaps after giving off more gluons. These found other short-lived quarks to interact with, forming new quark pairs and gluons again. Matter and energy were not just theoretically equivalent, it was so hot they were practically the same stuff. Somewhere around this time, matter won over antimatter. Today, we're left with almost all matter and nearly no antimatter at all. Somehow, 1,000,000,001 matter particles were formed for every 1,000,000,000 particles of antimatter. Instead of one massive ultimate force in the universe, there were now several refined versions of it acting under different rules. By now, the universe has stretched to 1 billion kilometers in diameter, which leads to a decrease in temperature. The cycle of quarks being born and converted back to energy suddenly stops. From now on, we work with what we have. Quarks begin forming new particles, hadrons, like protons and neutrons. There are many, many combinations of quarks that can form all sorts of hadrons, but only very few are reasonably stable for any length of time. Please take a moment to appreciate that by now, only 1 second has passed since the beginning of everything. The universe, which has grown to 100 billion kilometers, is now cold enough to allow most of the neutrons to decay into protons and form the first atom, hydrogen. Imagine the universe at this point as an extremely hot soup, 10 billion degrees Celsius, filled with countless particles and energy. Over the next few minutes, things cooled and settled down very fast. Atoms formed out of hadrons and electrons, making for a stable and electrically neutral environment. Some call this period the Dark Age because there were no stars and the hydrogen gas didn't allow visible light to move around. But what's the meaning of visible light anyway, when there's nothing alive yet that could have eyes? When the hydrogen gas clumped together after millions of years and gravity put it under great pressure, stars and galaxies began to form. Their radiation dissolved the stable hydrogen gas into a plasma that still permeates the universe today and allows visible light to pass. Finally, there was light. Okay. But what about the part we didn't talk about? What happened right at the beginning? This part can be defined as the Big Bang. We don't know at all what happened here. At this point, our tools break down. Natural laws stop making sense. Time itself becomes wibbly-wobbly. To understand what happened here, we need a theory that unifies Einstein's relativity and quantum mechanics, something countless scientists are working on right now. But this leaves us with lots of unanswered questions. Were there universes before our own? Is this the first and only universe? What started the Big Bang, or did it just occur naturally based on laws we don't understand yet? We don't know, and maybe we never will. But what we do know is that the universe as we know it started here and gave birth to particles, galaxies, stars, the Earth, and you. Since we ourselves are made of dead stars, we are not separate from the universe. We are part of it. You could even say that we are the universe's way of experiencing itself. So let's keep on experiencing it until there are no more questions to ask.
Okay, so hopefully that video turned out okay. My laptop almost choked on that. If you have any trouble with that, well, it is on Blackboard. The whole video is on the Blackboard website in the module for this chapter. Um, kind of summarizes what we've just discussed here. And so, yeah, there are a lot of unanswered questions, and there are some problems with the Big Bang model. We talked about how we think that the universe is at this critical density. And this is known as the flatness problem. Remember, we described the universe as having a flat geometry. And if it didn't have this critical density, well, then structures inside the universe could not have formed. And so we wouldn't have a lot of what we see around us if we didn't have this particular critical density. And there's also this problem that is known as the horizon problem. When we look at the background radiation, this cosmic background radiation that we see all around us, it's fairly uniform. There are some variations, as we showed you, but it's pretty uniform. And that's a bit of a puzzle because you have areas of the universe that are billions of almost 100 billion light years apart from each other. And so did these different areas, how could they have the same, almost exact same temperature if they haven't been in contact with each other? So that doesn't quite make sense, and that's known as the horizon problem. You have two things that are way out on the edge of your horizon that have never touched, and yet they're almost exactly the same temperature with a very high uh, level of precision. So that's a rather bizarre situation to be in. And so, how do you solve this problem? Uh, it's known as the inflationary hypothesis. Basically, what we think happened uh, very early in the history of the universe, during the first instant of time after the Big Bang, the universe grew. It inflated like a balloon almost. It grew by a factor of 10 to the 50th. So it expanded very, very rapidly. And so that kind of solves that particular horizon problem and the flatness problem at the same time. Uh, the universe was extremely small and everything was in contact. And then all of a sudden is expanded very, very rapidly. And the universe, the different parts of this universe are the same temperature. And they expand very rapidly. The universe gets this kind of flat geometry. And this kind of solves this inflationary hypothesis, solves this particular problem. And so this is known as the inflationary era of the universe. Just after the Big Bang occurs, the universe expands very, very rapidly. And that solves that issue. And so the flatness problem. Well, why does the universe have this flat geometry? Well, it's kind of like that. Remember that ant? We mentioned that two-dimensional ant. He lives on the surface of this ball. Let's say it's a balloon because it's expanding. Um, the ant only sees a very, very small portion of that balloon, and it seems flat to him, even though to us, as a three-dimensional creature, we can look at that balloon and obviously see that it's three dimensions, it has a certain size, it has a certain curvature, but the ant is not really aware of it because he only can see a small portion of it at a time. And so that's kind of the flatness idea. The same thing applies to the universe. It looks flat to us. And again, this is the sort of timeline here where this expansion is taking place somewhere here. And in this very early part of this universe, as mentioned in the video, and also as I mentioned, these very earliest moments beyond this 10 to the negative 43 second is really kind of unknown. We don't know what really happened here. We don't have the physics in order to understand exactly how the Big Bang occurred. And so, in order to kind of solve that problem, uh, how do we understand what happened uh, during when the Big Bang was happening? What caused it? How do we understand that sort of thing? What we need is a what's known as a grand unified theory. Uh, when the universe was very, very young, when the temperature was very, very hot, all the four usual forces of nature that we're familiar with, gravity, electromagnetism, the nuclear forces, the strong and weak nuclear forces that hold atoms together. These four forces of nature, in the very early moments of the universe, when the temperature and density was extremely high, those four forces unite. They come together, and they're merged. They're merged together, unified under these high temperature, high pressure situations. And so we can kind of the physics that we do have, we can unite three of those forces of nature. We can we can trace it back and we can unite those three forces. The problem is we can't unify gravity with the other three forces. So we don't have the physics yet to be able to do that. So we are missing some information that would really allow us to fully understand the Big Bang and the beginnings of the universe. And so we have basically two ideas here. General relativity, which talks about space-time, is Einstein's theory of general relativity, describes space-time and gravity and that sort of thing. And then we have quantum physics, quantum mechanics that deals with the very, very small of these quarks and how do these quarks make the particles that we're familiar with. And these two theories at the moment are incompatible. Uh, General relativity describes things very exactly. Quantum mechanics, physics describe things as probabilities. And so we have this little diagram that shows some different areas of physics. You have sort of the ordinary Newtonian type physics that we're all familiar with. And we have Newtonian gravity works very, very well. But in order to have a complete understanding of gravity, we have to have general theory of general relativity. If you want to understand things at high speed, near the speed of light, you need special relativity. And you've got these quantum theories, quantum mechanics, quantum physics that deals with particles. And the thing that we're missing, the missing piece of the puzzle is right here, quantum gravity. We are missing, we have no theories of quantum gravity really to link all these things together. We have a pretty good handle on how these other areas of physics connect together, but we're missing this critical piece. We do not have a theory of quantum gravity. And so that's what is a big project. Einstein himself was trying to work on this idea. He wanted to come up with a grand unified theory, sometimes abbreviated as GUT, G-U-T. And so we don't have that. One thing that has been worked on recently, more recently, has been string theory. And we don't have time to really go into the idea of string theory. I do have a short video on Blackboard if you'd like to learn a little bit more about it. And that's something that these theorists are working on. Can the string theory give us a theory of quantum gravity, or let us connect all these pieces together and finally understand where did the universe really come from? How did the Big Bang really happen? And this is not an answer that we can currently answer really here. Our question we can't answer. So string theory, interesting. One of our problems with string theory is there's many different versions, and we don't really have a good way of testing them and figuring out, well, which is the most likely situation, which is the most likely theory. We can't really answer that at this point, unfortunately. But that's something that these scientists are working on. So this idea that the universe has the properties that it does is often referred to as the anthropic principle. Is this just, the universe has these properties that are very beneficial to us? Is this just a lucky accident? The physical laws of the universe are what they are because if they were different, we would not be here. And that's called the anthropic principle. And so this kind of brings up the idea that's very popular in science fiction of a multiverse. Is our universe only one of many? Could there be other universes out there? And perhaps there could be. There could be other universes with other physical laws where the Hubble constant is different, or maybe the value of pi is different. Uh, the laws work differently. And some of those universes might immediately collapse. They might be closed universes, as we discussed. Or perhaps you might have accelerating universes that expand way too fast, as we mentioned, and maybe they expand so fast that structures like galaxies wouldn't form. Maybe stars wouldn't form either. And so that's a possibility. But unfortunately, this is just speculation. We might never really be able to answer that question, whether or not there are other universes, whether the multiverse exists out there, other universes exist out there. We may not be able to answer those particular questions. And so these are open questions. We certainly don't know everything about our universe, but we're certainly striving to try to understand the universe around us. And so I hope during this course that you've learned a little bit about the universe around us, and I hope you've enjoyed the course, and hopefully you'll think about some of these concepts when you next time you go out and look up at the nighttime sky. You might think about some of these things. And so I hope you have enjoyed the course and gotten something out of it. And so thank you for taking the course. And our final exam, as I mentioned, will be taking place as originally scheduled on Wednesday. And so I will see you at that point. If anyone has any questions about this chapter, please feel free to reach out. And so I will see you on Wednesday.